This video treats a topic called absorbing Markov chains. An absorbing Markov chain is a chain that has at least one state where you get stuck if you get there. A state like that is called an absorbing state. It's a state that has the property that once you get into the state, it's impossible to leave it. Here's an example of an absorbing Markov chain where state number 1 is an absorbing state. If you look at the transition probabilities corresponding to the first row, you see that when you're in state 1, the probability is 1 that you'll remain in state 1 and 0 that you'll go to either one of the other two states. So in this example, state number 1 is an absorbing state. Let's think about tracking students through a university. We have the 4 standard grade classifications: freshman, sophomore, junior, and senior. When a student successfully completes school, they enter the graduated state, and of course some students drop out. So we'll have the 4 states corresponding to the 4 class years. We'll have a graduated state, and we'll have a dropped out state. And the data that we're going to use in our example is what's shown right here in the transition diagram. So let's look at the transition diagram a bit just to make sure we're interpreting the numbers correctly. For someone who enters as a freshman, during their first year, there's a 10% chance that they will fail their year and remain classified as a freshman the following year. There's an 80% chance they'll successfully complete their freshman year during that year's time and move on to become a sophomore, or there's a 10% chance that they'll drop out. Notice that we don't have an arrow going from freshman to the graduated state because you can't graduate in 1 year. Nobody who's a freshman is graduated at the end of 1 year. Read through the rest of the transition diagram and make sure that you're clear on all the transition probabilities that are shown here. With seniors, for example, 90% of seniors graduate, 5% drop out, and 5% of them have to repeat their senior year. Notice also that nobody ever moves backward. 90% of juniors become seniors, but of course once you're a senior, you never go back to being a junior again. Now what about the graduated and dropped out states? We're going to treat both of those as absorbing states. If you look at the graduated state, we have a 1 on the arrow pointing from G back to G, which says that if somebody is graduated, then at the end of the next year they remain graduated. We're going to treat dropouts the same way. If a student drops out, then they're still dropped out at the end of the next year. In other words, they don't get readmitted to school. So that's a bit unusual. Most schools, of course, don't really have a policy like that. But for purposes of our example, we're going to treat both graduated and dropped out as absorbing states. And that leads to a transition matrix that has the pattern shown here. I'm listing the 2 absorbing states, graduated and dropped out, as states 1 and 2, and then the other states appear after that. And notice that the matrix has a particular pattern to it. If we list our absorbing states first, then we get a little identity matrix up in the top left-hand corner. The size of that piece will be determined by how many absorbing states we have. And then this upper right-hand corner has nothing but zeros in it. And then we have these other 2 pieces down here. The transition matrix splits into those 4 blocks. That will always be the case if you have absorbing states and list your absorbing states first. And we're going to be working with those 4 blocks. So we in fact are going to give them names. Since this upper left-hand corner is an identity matrix of some size determined by how many absorbing states we have, we'll call it I. And this top right-hand corner is just in this instance, it's 2 rows and 4 columns for this little matrix up in the corner. It's a 0 matrix of some size depending on how many absorbing and non-absorbing states we have. This bottom left-hand piece, which in this instance has 4 rows and 2 columns, is a matrix we'll call R. And then the bottom right-hand chunk, which will always be a square matrix, in this instance 4 by 4, we'll call Q. Now, what we're looking at on this slide is the transition matrix raised to the third power, approximately. I've done some rounding off here just because some of the decimal expressions were getting too long. So this is approximately t cubed. Let's think about the meaning, interpretation of some of these numbers that appear in the matrix t cubed. For example, the 0.612 here. That's the probability. Remember, we learned back in section 6.2 that for t cubed, the numbers in t cubed can be interpreted as the three-step transition probabilities. So this 0.612 is the three-step transition probability from the freshman state to the senior state, which, to put it in more natural language, would simply be saying it's the probability that someone who's a freshman will become a senior in 3 years. So that would be where a freshman would be in 3 years if they stay on track, right? Because the first year they would go from freshman to sophomore, the second year from sophomore to junior, and the third year from junior to senior. So this 0.612 is the probability that someone who starts as a freshman does make it to being classified as a senior within the 3 years time frame, which they would make it to that if they were operating on schedule. This little left-hand bottom piece is a special interest because it indicates the probabilities of hitting each of the two absorbing states, graduated and dropped out. For example, for someone who starts as a freshman, we're looking at three-step probabilities, so this would say somebody who starts as a freshman can't possibly graduate in 3 years, but there will be a 0.193 probability that someone who starts as a freshman will drop out within their first 3 years. Someone who starts as a sophomore has almost, or somebody who's classified as a sophomore, I should say, within 3 years has almost a 70% chance of graduating, about a 14% chance of dropping out. Someone who's a junior has almost a 90% chance of graduating within the following 3 years and about a 10% chance of dropping out, and so forth. So if you're interested in which state a student winds up in, this portion of t cubed is of particular interest if you're tracking the student for 3 years and wanting to know what has become of them by the end of that time. Now, an interesting question, and probably the most important question that can be asked, is if you're looking at the distribution of data that we have in the transition matrix, what kind of techniques can you use to determine the long-term probabilities for entering each of the absorbing states? It's obvious that you would want to know that, isn't it? Someone who's thinking about going to that school would be very interested in the question, if I go to that school, what are the chances I'll eventually graduate? There's hardly any information that would be more relevant than the answer to that question. Fortunately, there is a recipe for doing this, and we're going to track through that recipe. It simply involves some matrix operations. Remember, we sliced the matrix up into the 4 pieces shown here. Step 1 of the recipe is we're going to take this bottom right-hand chunk Q, which in our example is 4 by 4, and subtract it from the identity matrix of the same size. So in this matrix expression I minus Q, we're not really talking about this minus this because they're different sizes. Here, this identity matrix being referred to in this picture is a 2 by 2 identity matrix. So understand, when we're talking about I minus Q, we're talking about this 4 by 4 matrix Q, and we're talking about subtracting Q from the 4 by 4 identity matrix because you have to have two matrices the same size if you're going to subtract them. So the first step is a simple matrix subtraction. 4 by 4 identity matrix minus this 4 by 4 matrix Q. The next step is to find the inverse of that. Having done that subtraction, find the inverse of that, and that's what's called n. So the matrix n is the inverse of that matrix we computed in step 1. And then the final step in the recipe is to multiply the product n times this matrix R, and that product is called B. Let's think about the sizes to make sure that everything makes sense here. Q is 4 by 4, I minus Q is 4 by 4, so the inverse of that will also be 4 by 4. So N is a 4 by 4 matrix. In this example, R is a 4 by 2 matrix, so we'll be multiplying a 4 by 4 matrix times a 4 by 2 matrix, which of course is possible. And we'll get, when you multiply a 4 by 4 times a 4 by 2, you get a 4 by 2 matrix. So the matrix B that we're calculating in step 3 will in this example be a 4 by 2 matrix, 4 rows and 2 columns. In this example, when you carry out the recipe for I minus Q, we get the matrix shown here. R, we don't have to do any calculation to get that. We just copy it down from the original transition matrix. So we know what R is. Remember, we have to find the inverse of this guy. You can find the inverse of that using the matrix tool, and you come out with a matrix which, rounded off a bit, is shown at the top here. And then the final multiplication, n times R, this 4 by 4 times the 4 by 2 matrix R that we saw on the previous slide, and we come out with the product matrix B that looks something like what's shown here. This is the matrix that contains a lot of valuable information. To interpret that information, what we do is we label the rows of B with the names of the non-absorbing states in the same order that we had listed them in the original transition matrix: freshman, sophomore, junior, and senior. These were states 3, 4, 5, and 6 in the original transition matrix. So we label the rows with those same states in the same order, and we label the columns with the names of the 2 absorbing states, again taken from the original transition matrix, keeping the same order. We originally had these as states 1 and 2 in the original transition matrix. So there are column labels. With this labeling, the numbers in this matrix B can be interpreted as the long-term probabilities of going from any of the non-absorbing states into either of the absorbing states. For example, the 0.753 says that there's about a 75% chance that someone who enters as a freshman will eventually graduate. About a 25% chance they'll drop out instead. The 0.898 in its position is saying that for someone who is currently a junior, there's almost a 90% chance that they will eventually graduate and only about a 10% chance that they will drop out. So obviously the long-term prospects of a junior are better than the long-term prospects of a freshman, simply because they're already much closer to graduation. So the important point is that the numbers in the matrix B show the probability of eventually arriving in each of the absorbing states, depending on which column you're looking at, from any of the non-absorbing states, depending on which row you're looking at. The 0.102 is the probability that someone who is classified as a junior will eventually drop out rather than graduating. Now to move to an entirely different example. Sally and Becky are playing tennis. Deuce is a score in tennis which says that in the game that's being played, the 2 players are tied with the same number of points. And then at that point, somebody has to get 2 points ahead in order to win the game. Now the assumption we're making in this example is that when the game is tied at deuce, Sally has 2/3 probability of winning the next point and Becky has 1/3 probability of winning the point. On the other hand, when Sally has advantage, which means she's a point ahead, then she has probability 3/4 of winning the next point. When Becky has advantage, that is when Becky's a point ahead, she has probability 1/2 of winning the next point. So the probabilities of either of them winning the next point depends on what state they're in relative to the score. So we're going to set this up as a Markov chain with the states being, absorbing states will be Sally wins the game and the game is over, or Becky wins the game and the game is over, or Sally's advantage where Sally's a point ahead, or Becky's advantage where Becky's a point ahead, or deuce where the score is tied. So the play can go on for a long period of time. It has to go on until somebody gets 2 points ahead. That's the nature of the game of tennis. One of the questions we'll look at is if the game is at deuce, find how long the game is expected to last and the probability that Becky wins. And then a second question we'll look at is that if Sally has advantage, that is if Sally's a point ahead, what's the probability she eventually wins the game? So we set up names for the 5 states. The game can be at deuce, it can be Becky's advantage, Becky a point ahead, Sally's advantage, meaning Sally's a point ahead, or Becky wins, which is an absorbing state because at that point the game is over, or Sally wins, which is the other absorbing state because again the game is over if somebody has won. The transition diagram is as shown here based on the probabilities that we saw in the original setup. If the game is tied at deuce, there's a 2/3 probability that Sally wins, so the score goes to Sally's advantage. There's a 1/3 probability that Becky wins the point, so it goes to Becky's advantage. If it's at Sally's advantage, there's a 3/4 probability that Sally wins the point, so Sally wins the game. There's a 1/4 probability that Becky wins the point, so it goes back to deuce. If it's Becky's advantage, then there's a 1/2 probability that Becky wins the point, so Becky wins the game. There's a 1/2 probability that Sally wins the point, so the score goes back to deuce. So check all the numbers in the transition diagram here to make sure that you agree that the transition diagram we've drawn is consistent with the information we had to start out with. Putting those numbers into a transition matrix, the transition matrix is the one that's shown. The top left corner is 2x2 identity because we again have 2 absorbing states. All zeros in the top right piece. The lower left block R has 3 rows and 2 columns. And the matrix Q in this example is a 3x3 matrix. So following the recipe, we start with Q, subtract Q from the 3x3 identity matrix, which takes us to here. R is just the lower left block we've copied over. And then we find the inverse of I minus Q, again a 3x3 matrix, which is the matrix shown right here. The multiplication that's done is to multiply that inverse matrix N times the block R, which was taken from the lower left corner of the original transition matrix. And the result of that matrix multiplication is the 3x2 matrix shown here. The number of rows is the same as the number of rows of non-absorbing states that we had in the original transition matrix, and the number of columns is the same as the number of absorbing states. So we label this matrix B with the row labels coming from the non-absorbing states in the same order as in the original transition matrix, and the columns being the absorbing states. N itself is a square matrix, and we label the rows and columns of N with the names of the non-absorbing states. Now, all the information we're interested in problems that have to do with absorbing Markov chains, all the information we're interested in comes from one of these two matrices. The long-term probabilities come from the matrix B. The meaning of the 1/4 is that if the game is tied at deuce, which is one of the non-absorbing states, then the long-term probability that Becky wins the game is 1/4. The long-term probability that Sally wins the game is 3/4. Another way of saying that in a natural fashion is to say, if the game is at deuce, Becky has a 1/4 probability of eventually winning the game, whereas Sally's probability of eventually winning the game is 3/4. If it's Becky's advantage, then the chances that Becky eventually wins the game is 5/8, Sally's 3/8, and so forth. So this is where we go to get the long-term probabilities based on whatever assumption we want to make about which non-absorbing state we happen to be in. We're also, in this example, going to illustrate use of the matrix N. The numbers that appear in N represent long-term expected values. For example, the 3/4 says that if the game is at Becky's advantage, so Becky's a point ahead, then the expected value for the number of times the game will be at deuce prior to somebody winning the game is 3/4. The 5/4 in the bottom right-hand corner says if the game is at Sally's advantage, so Sally's a point ahead, then the expected number of times for that to be the score, in other words, the expected number of times that the game will be at Sally's advantage prior to somebody winning, is 5/4. Notice that all of these numbers are bigger than 1. They have to be at least as big as 1 because, for example, if you're at Becky's advantage, then that's already one time you're at that score. So you'll be at that score at least that one time before the game ends. And in fact, this number is 1 1/4, 1.25. So the expected value for the number of times you'll be at that score before the game ends is a little bit bigger than 1, because it could go from Becky's advantage back to deuce and then back to Becky's advantage again. The other interesting thing about this matrix is that you can add up the numbers in any row to get the long-term number of steps for the game to end. Looking at row 2, we're looking at the scenario where it's tied at deuce. On average, the score will be Becky's advantage 0.5 times before the game ends. It'll be deuce 1.5 times before the game ends. And it'll be Sally's advantage 1 time before the game ends. If you add up all those numbers, you have the expected value for the total number of points played prior to the game ending. So in this case, you add up the numbers in the second row and you get 3. So that's saying that if the score is tied at deuce, then on average they're going to play 3 more points in order for the game to end. The game could end in 2 points. Sally could win the next 2 points and it would be over. But it might go back and forth and back and forth and back and forth. They might play a large number of points before the game ends. It averages out to 3. The expected value for the number of points played, if it's at deuce, the number of points played for the game to end averages out to 3. You could similarly add up the first row or the third row to find the average number of points to be played if you're starting from Becky's advantage or from Sally's advantage. If you go back to the example of tracking students and think about that same kind of question, In that example, the matrix N turned out to be what's shown on this slide. And if we go back and label N with the labels from the non-absorbing states, freshman, sophomore, junior, and senior, then what you have is the average number of years spent at each of the classification levels prior to either dropping out or graduating. So let's look at some of these numbers and interpret them. Let's look at a freshman. What does this number say? It says on average, a freshman will spend 1.11 years classified as a freshman prior to either dropping out or graduating. So we know there's 1 year because they're already a freshman right now. So that year will contribute 1 year, but there's a possibility of more than one because they may fail their freshman year and have to repeat it again. So on average, freshmen spend 1.11 years classified as freshmen. What about this 0.884? The freshman might drop out before ever making it to the junior year. So they may never transition through the junior year, which is why that number is less than 1. There's no guarantee that they'll be ever classified as a junior. Of course, they may be a junior more than 1 year. They may be a junior, fail that year, and have to repeat as a junior the next year. So it's possible that a freshman could spend more than 1 year as a junior, but it averages out to a little less than 1 year because some freshmen never make it that far, and even less for a senior. Why is there a 0 down in this spot? Well, if somebody's already a junior, then the expected value for the number of additional years they'll spend as a sophomore is 0. They'll never go backwards to being a sophomore. If someone is a senior, why is this number a little bit bigger than 1? Well, they're already guaranteed their 1 year as a senior since they're already a senior. And if they fail their year, they'll have to repeat as a senior the next year also. So that has a small probability of happening, which means the average will be a little bit more than 1 year that a senior will be in the school. Let's think about the row sums. If you add up the numbers in the first row, you get about 3.8. What is that saying? It's saying that for somebody who is a freshman, if you add up the expected value for the number of years they'll spend as a freshman, sophomore, junior, and senior, you get about 3.8 as the expected value for the number of years they'll spend in school. Now, of course, it'll take them 4 years at least to graduate. So for somebody who's graduating, it'll be 1 year as a freshman, 1 as a sophomore, 1 as a junior, 1 as a senior guaranteed, possibly additional years if they have to repeat any grades. But on average, how can this average out to be less than the 4 years required for graduation? Well, it averages out to that simply because some students drop out before graduating, so they're in school for a much shorter time. So remember, these are averages, expected values. For somebody who's a sophomore, of course, if you look at the number of years to graduate, if they're going to graduate, then they'll spend the sophomore, junior, and senior years doing it. So that's at least 3 years. Not all of them will graduate, but for somebody who has made it successfully to the sophomore year, the expected value now turns out to be a little bit more than 3 because the chances of somebody repeating slightly more than offsets the possibility of dropping out. So some of the sophomores will spend less than 3 years because they drop out. Some will spend more because they have to repeat. It averages out to a little bit more than 3 years. And similarly, the junior row sum indicates that on average somebody who's a junior will spend a little more than 2 years in the school, and for seniors 1.053.